Hello everybody. So today we talk about the system design of a bit tree, and this is the part two of this my video about the bit tree. Okay, so today we talk about these two topics. So number one, how to make URL short and unique. So this comes from these two non-function requirements. I didn't talk last time, and also I will talk about the scalability. This one. That being said, let me get started with the first one. Okay, so the URL is created here in this URL generation service. So when user makes a request to create the new short URL, this URL generation service creates a kind of alias here and then try to store it in the database. But if the alias has been taken, that alias has been taken by any other URL, which means this alias unique constraint is not met, the write to the database fails. So what this service can do is retry. So it can retry, let's say, creates a kind of random value here, and then retry to write it into the alias. And if when it does again and again and again, finally it can find the value which is unique, so it succeeds as a writing. Creating the recode, so it now returns the, short URL to the user. But obviously there is a problem here. So the first thing I can say is, in the worst case, this URL generation service keeps retry again and again and again. And if that happens for many servers, this database should be overloaded. So I have to think of the smart way to make this kind of alias creation to be unique. So I will tell a few ideas. So the first idea is using the Snowflake ID. I will list it first. So the second idea is using the sorry, I actually started from using the random value here. The second idea is use Snowflake ID. The third idea is use kind of counter. Yeah. Okay, so as I said, I don't go with this because it can cause the collision often in the worst case. Yeah, so I can use, there is a smarter way to avoid the collision logically. So I will talk about the Snowflake ID approach. Okay, so I searched with Snowflake ID, and this is the result of the image search in Google. So this is a Snowflake ID. So it's the 64 bits ID, and the first one is the, as you can see, sign bit always 0, and there is timestamp, machine ID, and sequence. So I can say this is ordered by the timestamp for this part, and also because there is a machine ID, and also there is a sequence number here. So I can say they should never collide each other if each server creates the ID with their Snowflake ID. But of course, this is not perfect, obviously, because as you can see, this and this part represent the millisecond timestamp, kind of. And this one has the machine ID. And I can say machine ID is from 0 to 1023. So if there are more than 1023 servers, we have to use the modulo of 1023. So it is possible that this machine ID collides between different servers. And also, even in the same single server, or maybe the servers whose modulo are the same, when I take a look at this timestamp, and sequence, it can collide if the ID is created exactly as the same millisecond timestamp. So yeah, what I mean to say is I cannot avoid the collision completely, but the probability of the collision is much smaller. Yeah. So with using this Snowflake ID, I can say this randomized URL randomness is easily met. I should rephrase. So when we meet the randomness, we can create the ID without collision so quickly, meeting the randomness. Yeah. And of course, if there's a collision, as I said, this unique constraint causes the error of the right query. So now this URL generation service can create another Snowflake ID and write it again. Yeah. So that's what happens. But as you can see here, Snowflake ID is quite long, like this binary. So there are how many numbers? So I can say there are 2 to 64 unique values. Oh, sorry. So if I put the number, if I use just a number, let's say with 10 base, there's this number of unique values. So 2 to the 64 is, I don't know. Okay, so 2 to the 64 is this. So the URL become this length. This is kind of too long. So what I can do is using the base 62 encoding. So with base 62, each character, each letter can be number 0 to 9 or A to Z or uncapitalized A to Z. So 10 plus 26 plus 26 is, 10 plus 26 plus 26 is 62. So I can say with base 62, this number becomes 2 to the 64, and I take the log 62. So I can calculate this in this way, so it's around 10 to 11. So we need 11 letters. So this is a kind of short compared with obviously this. I don't know how many digits this is. Yeah, but still I can make it shorter because we don't need this number of URLs. We need only how many? 1 billion. So 1 billion is something like, so this is 1,000, a million, billion, so only this, yeah. So this is much shorter. So what means is that Snowflake ID uses 64 digits. but it's too many. So what I can do possibly is, let's say I make this sequence number a little granular, and also maybe machine ID more granular if we don't so many machines. So in that way, I kind of compact this and create the custom style snowflake ID and use it. In that way, we don't support this number, but probably it should be much big enough from compared with this number with some buffer. Then when I take the base 62, it should be smaller, maybe 789. So that's something I can use here. So the kind of answer here is use the customized snowflake ID, or I should say snowflake style ID. Yeah. So get the random number, and then I do the base 62 encoding to get the shorter sequence. Okay. So now I could talk about the how I can meet this URL should be short and random. Yeah, but I want to introduce one more idea here using the counter. So what I can do here is, let's say when this URL redirect service just uses a counter. So the first, this one, sorry. So for the first URL request, it uses counter 0, the next one 1, next one 2, next one 3. So in that way, we can increment the number, and I can guarantee that there shouldn't be the collision because we, get the number with the counter incrementally. So with that, I can store this number into this original alias. So firstly, I can say in this way, URL can be random. Shorter URL can be random. But the problem here is, again, in the same way as this snowflake start ID, when I think of the 1 billion, it becomes something like this, maybe 10 digits. So it's too long again. So I can do completely the same thing. I do the base 62 encoding here. So with this, completely the same thing happens, and the URL should be 67. Yeah, I just mentioned that this is a kind of problem here because I said using the counter, this URL is random, but it isn't obviously because it's counted. So with base 62 encoding the URL, still this is obviously sequential, yeah, not randomized. So I have to think of the way. So what I can do as the toric is kind of using the function to get the number to number. So firstly, I get the count sequence number with the counter, and then map it into another number in, yeah, and this argument should be 1 to 1 billion, and this returned value should be 1 to 1 billion. So in that way, the sequence number is mapped into another number between 1 to billion. Yeah. Then I can do base 62 encoding on that number. Of course, this function is something the user can find out, but yeah, still I can say this is much randomized for ordinary users, let's say non-mathematicians. So yeah, I think this is good enough. Yeah, obviously, the purpose of this service is not to make the URL completely random and avoid the hacking. Yeah, so when it is randomized enough, I think it's good enough. Okay, so in this way, I can do the, create the randomized URL with short alias. Yeah, okay. Oh, I need the, okay, I will talk about this counter approach from here because it's more interesting, I can say. So I use the Redis counter here. So this generation service should get the counter, the number from here. So this, what it does is increment plus fetch. Yeah. This increments the number, let's say like 100. Then gets that range from original value to original number to the number plus 100. Then this URL generation service is assigned those 100 numbers. So now this generation service doesn't have to call the counter for each generation. So I'm almost talking about the scalability, but I will continue. So that's what I can do for the kind of, yeah, scalability. And also I'd like to make sure that even if there are multiple services, multiple servers for generation service, the counter is not, there isn't a race condition because Redis is basically single threaded and it accepts the request one by one in a kind of serializable way. So there isn't a race condition that, like the different servers which requested at the same time are assigned the same range of number. It doesn't happen. Okay, so yeah. Now I will talk about the scalability. So I will talk about the scalability from three perspectives. So number one, throughput. Number two, spike of the throughput. And number three, storage size. So this is the number. So firstly, I do the back of envelope estimation. So there are 100 million data active users. So this is not clear if this is number of generated URLs or number of redirects. But I will assume that this is the redirection number. And I don't talk about the generation. I can say this is quite steady. Yeah, because let's think of the usage pattern of this service. I can say the URL generated is clicked by many users, especially if the generated URL is included in the post of the celebrity, like Taylor Swift. For one URL, there are millions of users clicking it. So this is quite read heavy, so I will focus on the read request. So 100 million redirects per day, because one day is around 10 to the 5 seconds. So this should be 1K requests per sec. So there are 1K, the throughput of redirect is 1K. So actually this is totally fine. This request goes to rooted in, the redirect, request for the short URL is routed into this server and then routed into primary DB. And for API gateway, this is horizontally scales internally because this is, practically the fleet of servers. And for this URL redirect service, typically easy to get handle 1K requests per sec, so one server is good enough. But maybe I can do the horizontal scaling for the spikes I will talk later, and also especially for the availability. Even if one server goes down, there is another server which keeps working, so the system doesn't go down. And 1K requests per sec, PostgreSQL can handle this with single node. But again, I would introduce read replica here. Again, the reason is for number one for spike and number two for the availability. So even if the primary node dies, the PostgreSQL, we can set the kind of auto failover configuration on this PostgreSQL, and read replica is promoted to the primary node. So the downtime should be maybe less than 10 seconds in that way. So that's something I can do for availability. Yeah. And also I added the index on this alias column, so the record access is log time, so this is pretty fast. So yeah, I can say in this way the redirect is fast enough. And now I will talk about the spike. So let's say 1K requests per sec becomes 100 times. Yeah. So this happens, as I said, when the short URL is included in the post, which became viral. So in this case, the problem occurs. So typically, PostgreSQL cannot handle 100K requests per sec with single database. Yeah. So what I can do is introducing the Redis cache here. So I can use it as the read-through cache. So read-through cache means, firstly, this URL redirect service takes a look at the Redis cache, and if there isn't a data, it fetches the record from PostgreSQL and then stores the data in Redis and then returns the response. Yeah. So Redis cache can handle around 1 million requests per sec, in my understanding. So I told her right. So around 100K requests per sec. Yeah. So yeah, this can handle this spike. Yeah. So I can use it. Okay. If this is, yeah, okay. So for server, we can auto scale this server to 100 servers. So typically, as I said, one server can handle 1K requests per sec. So only when the spike occurs, we can auto scale the servers according to the memory usage or maybe CPU usage, and then 100 servers is horizontally scaled. I mean prepared. So in this way, requests are handled by server, and yeah. Now I can say this. Yeah. So that's what happens. So of course, if this Redis cache is not fast enough, because of the request. What I can do is for each, for on this server, physical server, I can boot up the Redis server internally in each server. So in that way, the number of requests made to this internal Redis is exactly the number of requests each physical server handles. So it should be 1K requests per sec. So in that way, Redis doesn't become the bottleneck. Okay. Yep. So that's how I can handle the spike. Okay. So now I'll talk about the storage size. So because we have the 1 billion URL, and let's say each record here, URL mapping is 100 byte. So in this case, this becomes 100 kilobyte, megabyte, gigabyte. Yeah. So this is small enough to be stored in the PostgreSQL, because nowadays PostgreSQL can store 100 terabytes of data, hundreds of terabytes of data. Yeah. So this is totally fine. Yeah. Okay. Redis 2, 100 gigabytes is completely fine. So actually this can cache all the existing URL mapping here. Yeah. Okay. Good. So that's how I can scale this service. Okay, so one more thing I should mention is about the CDN. So when I think of the scalability, especially for the read request, what we can do is introducing the CDN cache. So CDN is the edge location which stores the request response. And the good thing is this edge location can be physically close to the user. So when I request when I make some request from Japan, the data is returned from the edge location in Japan. So it physically close. So the benefit, latency is really low. Yeah. So that's the benefit of CDN. But I don't use the CDN here because, as I said in here, we want to correct the metrics. So we want our users' request to come to at least this server. So in that way, I can say we can correct the metrics. So for that, I don't use the CDN here. Yeah. Okay. Okay, good. Maybe one more thing I'd like to mention is if user sets the expiration time in this request, for this Redis cache, the mapping record with expiration should be set with the TTL, time to read. So in that way, when the expiration is over, the record is deleted from Redis cache. So yeah, that's something I can do. Okay, that being said, I finished my today's system design practice. Thank you so much. Bye.